So this is our Friday seminar, and my name is Yu Zhang, and I'm a professor in the Department of Civil and Environmental. So today we have Dr. Qing with us, and he's also a member from our department. And his research focuses include the sustainable transition infrastructure, facility design and management, primarily in the road system, pavement structures, and asphalt materials. Dr. Liu serves as one of the associate editors for the journal Translation Research Part D, Transport and Environment. And also he's the chair for the academic committee of the International Association of Chinese Infrastructure Professionals, IACIP. Dr. Liu is a member of the SCE EMI, which is EMI Mechanics of Pavements Committee, and also serves on several editorial boards for different journals. And Dr. Liu holds the bachelor degree in highway and urban road engineering from Southeast University in China, and also his master's degree in statistics and his doctoral degree in civil engineering from UC Berkeley. So before joining USF, Dr. Liu actually was a project scientist and a lab manager at the UC Berkeley University of California Pavement Research Center, which is called UCPRC. And Dr. Liu is also a professional engineer in civil engineering license in California. So please join me to welcome Dr. Liu.
Thank you for the very detailed introduction. I'm very glad to have this opportunity to share the research that have been done by me and my team over the last several years, like over the last decade, pavement along the line of pavement surface materials. And so this is like the first seminar in this semester's seminar series, and you can see that this seminar series was co-sponsored by the Department of Civil and Engineering and and several university transporting centers, and also marine transportation, and also USIP student chapters. So today I'm gonna introduce the research that has been done by me and my team over the last decade, and from different approaches, including the field data capturing and analysis, and lab experiments, and also modeling methods. So the topic is focused on the pavement surface mixtures, specifically the porous asphalt mixtures. So what is porous asphalt mixtures? Before that, I want to introduce the development functions of pavement surface. And you can see on this slide, when we design a pavement structure or pavement surface, there are several development qualities or functions that are required by different group of people. Like for example, from the user's perspective, we want a pavement surface to be smooth and not to be safe, which means it needs to have high skid resistance during raining or favorable weather conditions. And from a structure perspective, we want the surface to be durable, last for a long time without major rehabilitation or maintenance. And there are some other desirable properties, including like tightness. We want a pavement to have low traffic noise, and also we want a pavement to be able to control the stormwater runoff during heavy rains, and also want a pavement to be visible in heavy rain, so we have high visibility and low stational weight. So you can see that a number of design functions for the pavement. Some of the functions are kind of complicated with each other. So we need to achieve some trade-off between these different aspects of design functions. Now, among all of these functions, most of them, I think that can be reached by sort of the porous asphalt or porous pavement surface. So this is what it looks like. A porous pavement surface, it looks like it's a magnet or porous, high airflow content. And the porous pavement surface can be achieved by the use of porous mixtures. And commonly we use two types of materials for pavement surface or pavement construction, including asphalt mixture and the stand-on mixtures. And both materials can be used to produce porous porous mixtures, and you can see the sample, picture of sample of both materials here. And they have the same feature in that they have high, sort of high porosity or high air buffer again, in range of 80% to 35% of the volume of the compacted mixture. And this is mainly achieved, this higher level of porosity is mainly achieved by the use of the selection of the specific distribution of aggregate sizes. Okay. Now, here in the United States and in many other countries, most pavements, over 90% of pavements are paved with asphalt materials. So my work will mainly focus on the asphalt mixtures, porous asphalt mixtures. Porous asphalt mixtures, as I mentioned, that the high porosity is mainly achieved by selecting a specific distribution of aggregate sizes. Now, for pavement for asphalt mixtures, there are a number of asphalt aggregate gradations that are commonly used. For example, here I show a gradation line for dense graded asphalt mixtures. Here, this is like this price similar to like cumulative distribution function of the aggregate surface. With the x-axis is raised to the power of 4. So such that a line close to the line of identity will give us a mixture that has high density, so that is called a dense graded. So we'll have the compact mix will have a low, or will have a low level content, and that will have a high density. Now for the open graded gradation, which the CDF aggregate gradation line looks like this. So when you can imagine from CDF to a PDF on the next buttons have a PDF at aggregate size. So for this mix, we may consist of coarse aggregates while with little contents of fine and then medium aggregate sizes. Or there's another commonly used aggregate gradation, which is called the gap gradation. The example of CDF looks like, so from here, you can see that there are two pieces taking the probability function, which one should be at the small aggregate size, another piece is at the large aggregate size. So for this type of aggregate gradation, it has a high content of coarse aggregates and also high content of fine aggregates. Okay. So these three aggregations are commonly used in asphalt mixtures for pavement construction. Now, for the porous asphalt mixture, which you use an open with aggregation. Now, it is not a new mix. It has been used for several decades, and it has been mainly used in two applications. First is commonly used in at a high friction force known as the OGFC, open graded friction force. That has been used since 1950s in the United States to mainly to improve the wet weather friction, okay, to reduce the hydroplaning during rain, to reduce the on-film thickness on the surface of the human plane. So for this application, so you can see that the layer of OGFC is placed on top of some underlying dense graded asphalt mixtures or pavement layers, and when you're going fall down to the surface of the pavement, then the high quality from the OGFC layer will allow the water to move quickly away from the pavement surface, so that the water film thickness is reduced, so that the hydroplaning potential is reduced. Another application is the use of the OGFC or the porous asphalt mixture on top of some porous, high permeable underlying layers. So this pavement structure is called the permeable pavement structure. So this application is mainly is used to control the stormwater runoff payments, and it has been applied in regions like the parking lots and the shoulders or sidewalks. In here, you can see many examples here in temporary areas. So when water in rain falls down to the surface of pavement, then water can bring to the underlying process based on the soil base. Here, in the OGFC, which is applied as a friction force on the surface, has been widely used here in Florida, and it has a particular name called FC5. And based on the FTSS pavement design manual, the FC5 is required to be applied on all pavement of all roads with the design speed 50 miles per hour or higher, and with two or more than two speed, more than two lanes in one direction. Okay, so here we see, I took this screenshots from the map. We see that on East Fowler Avenue, just near the US campus, the west of the full speed down section of the East Fowler had a speed limit of 45 miles per hour. So it is not required to use the SC back of Porous Asphalt and the surface. And you see that this is against with critical force. On the west side of the full speed down, then the speed limit is 50 miles per hour, and you can see that it is required to use the SC5, which is the Porous Asphalt mixture. But we may not be able to see very clearly the differences between the two different surface materials, but if you go there and if you walk around the road, then you can see the differences. Okay. Now, the Porous Asphalt mixtures are desirable to control the water thickness and also have achieve some other benefits, like to reduce the high-frequency noise and to reduce the stress and spoil, to increase the visibility during rain and night. But it has some issues. The main issue is that because of the high porosity of the mix, so the integrity of the mix is reduced compared to the dense grade mix. So typically they have a short service life. Typically the service life is like 7 to 10 years. Okay? And the major failure mode is the rubbery of the aggregates, coarse aggregates in the mix. Okay? And there are some other issues like clogging and like cracking. Okay? And now in the current design of the old DLC, like over the force of the pavements, other side benefits like the acoustic performance is not considered in the next design. Now, so the objective of the research done by me and my team over the last 10 years is mainly to design porous asphalt mixtures for to improve the durability, so it can last longer, and also for consideration of the acoustic performance, so that we wanted the pavement surface to achieve a high level of tightness. So the research approaches mainly include like making field study, lab experiments, and modeling. So the field study that I was involved in actually began in California for the project scientist at the UC Pavement Research. So over there, we was involved in a multi-year project that looked into the performance and probably of the pavement surface mixtures across the United States highway system, and basically we collect the data from over like 70 pavement sections selected artificially to cover different types of pavement surface materials and to cover different level of traffic volume and the different type of climate conditions. And here are the 4 typical pavement surface mixtures that are included in the study, which is first one is the sweet asphalt mixture, and this one is open grade of porous asphalt mixture, and this is the gap grade like through peaks in the product as function of the aggregate size distribution. And this one has the rubberized asphalt, so it's called a FC, rubberized asphalt free with gap gradation, and this is another open grade asphalt mixture with rubber asphalt in black coat. So the field study includes like a field condition survey, including like condition survey, measurements in the normal traffic speed, and we measure the noise between the time surface using the OBSI method, and we measure the pavement surface smoothness using the data sensor and also the macro texture, and then the pavement section will also code for like institute testing, including like pavement surface condition, visual inspection, and measurements of permeability, friction, and sampling, so recording, and the core samples are brought into the lab and for further lab experiments, including the determination of the layer thickness, airflow content, and insulation, and measurement of the sound absorption. Now here we see that there are 2 methods that were used to measure the sound related performance. One is the field measurements in terms of the OBSI, and that approach is depicted in these pictures. So in this approach, we put like a pair of microphones near the interface of high and thin surface and then measure sound intensity. Okay. And in the lab, we like use this sort of impedance tube test in which we like this for sample in this metal tube, and we send a white noise signal to the surface of the sample, and then we connect with some pressure that you see that is reflected by the specimen surface, and we can calculate some of the sound absorption coefficient. So the higher this coefficient, then the more capable that the mix can absorb some energy, okay, or to reduce the noise. So why are we so interested in the type of noise in the field? That's because the trapped noise on those mainly comes from the three sources. One is the as I showed here, one is the noise from the engine and from the exhaust powertrain system, the power noise. Another sort of noise is the aerodynamic noise, which comes from the vibration of air around the vehicle. The third source of noise is the type of pavement noise. Okay. Now, this chart shows that with the increase of the speed of the vehicle, the car or the trucks, the type of noise began to dominate the total traffic noise. Okay. So these are some first of the speeds in which the type of noise began to dominate the total traffic noise. So that if we can reduce the type of noise, we can significantly reduce the total traffic noise on the roads, particularly at high speeds. So that we can reduce the type of noise and the source of the noise. Now, these are the findings from the field study. Basically, we had about the measurements of the on all the sound intensity noise, but here OBSI for the noise measured in the field between the time and pavement interface. And the overall means that it's overall the average across different frequencies of noise. And generally, we found that the power spectrum different from the DAC or FO has a lower type of noise than the dense wave or gap wave. And over time, the noise reduction benefit begins to diminish. After 7 years, the ODS, the OGAC has a level of noise kind of similar to the other mixes, like the BGAC and the gap wave mixes. But the mix with rubber can retain the noise benefit for a bit longer, like 2 years. So these are some like exploratory analysis, and we want to next find some quantitative results. Okay. And then we want to look at the relationship between the event parameters of the materials and the noise. And so we use the multi-year measurements of the OBSI, the type of noise from around like over 70 seconds, which consists of sort of panel data. So for the panel data, there are like econometric models that are actually the panel data. In our study, we're going to use a two-way random effect model. So we consider like some random effect around the different sections and also across the time. And for the field data, collects from like in-service payment sections or from other in-service infrastructures. One common issue is that the variables, the independent variables, sometimes they are not totally random. Then for example, the payment surface data signage is not selected randomly. It is designed based on inputs like the traffic map and the climate condition and maybe soil condition. So for the field data, we don't have observation of some relevant independent variables like the soil quality and some other variables. So that in this case, these kind of variables like the signage will be correlated with the random error term, which include the sum of the survey random. So this is part of the indigeneity issue. So to address this indigeneity issue, we kind of use some instrument levels. So kind of we kind of use the regression model and some multi-moment registration model to convert like a different payment layer thickness, airflow content, and the mix type selection to some exogenous variables like the traffic level, traffic volume, the age. So with that, we kind of now we kind of results and which the results show that the time human noise increases with the payment age and with the payment macro detection, which is the meaning profile test. And also the time human noise decreases with airflow content in the payment surface mix and also the surface layer thickness. And these are kind of so these findings are kind of what we expected. Now, in terms of the four mixes, and they are relative performance in terms of the noise reduction, is that the open grid mix with rubberized asphalt performs the best, and followed by the regular porous asphalt mixture, and followed by the RACT, and followed by the dense grid mix. Now, this field study developed some findings, but the field study is expensive, and we don't have any control regarding these variables that we observed, and also we missed the observation of some variables. Because we do not have observation, or we cannot observe some variables. Okay, and also the sample size is limited, and so the findings from the field study do not have much on the design details of porous asphalt mixtures. For example, how to increase the level and mixture design, how to adjust the air prediction, achieve the desirable level of airborne content. So to address these issues, and we performed a lab experiment, like lab study that includes a number of lab experiments. And the objective of the lab experiment is to investigate the mixture design parameters on the porous asphalt mixture performance in a controlled environment. And the performance in terms of the acoustic performance, durability, friction, and permeability, and the design parameter of the mix includes aggregate relation and content and type. So there's quite a lot of detail here, but I'm not going into detail. But we're going to include over 20 different mixtures with 94 hungry mix and some dense grid, some gas grid mix, and we have multiple experiments to address different objectives and evaluate the effect of the size of the aggregates, maximum size of the aggregates, evaluate the effect of the aggregate content, the aggregate shape, and aggregate type, and additives, and some other promise and mixtures. So we included the four different aggregate gradations in the experiments, and with like different nominal maximum aggregate size from 4.75, which is very small aggregate size, like a 0.2 inches maximum aggregate size, and then to a maximum aggregate size of 19 millimeter, which is like a 3/4 of an inch. But here, how many in practice the nominal maximum aggregate size of 9.5 or 5.5 and are used in practice, but the 4.75 not widely used. So anyway, we include them in the experiments, and then the finding that may not detail in the test result, but the findings in terms of aggregate size, the fact is that the aggregate size with the reduction of the aggregate size, maximum aggregate size, we see that the reduction of the air, reduction in the permeability, and also the reduction in the even surface macro texture, and but in terms of friction, there's a large influence of the aggregate size of the pavement surface friction. In terms of the sound absorption, the change of the nominal aggregate size will change the peak frequency. Will change the frequency where the peak absorption coefficient first, and also will change the overall shape of the sound absorption coefficient spectrum. While with the reduction of the aggregate size, then we see that the peak absorption coefficient is reduced. And then in terms of the strength, the effect on strength of the mix, then the reduction of the aggregate size can increase the strength into the tensile strength in terms of the resistance to rubber, and also in terms of the resistance to combination effect of moisture and repeated traffic loads. Okay. So not much in terms of that we think there's some improvements. Okay. So we see the benefits in the use of small aggregate size in the production of the porous asphalt mixture, and with some reduction in the permeability and hematologic architecture. And now for the internal binder for modification effect, we looked into different binder types and binder counting. Here, this plot shows the result of the effect of binder types on the resistance to rubbing of the mix. And generally, we see that the use of the polymer modified binders, and represented by these three sets of bars, they can significantly reduce the rubbing potential or improve the resistance to rubbing, so that it can improve the durability of the mix in the field. Okay. And asphalt roller can also improve the durability compared to the modified asphalt binder. And then in terms of the rolling resistance, the polymer modified binder can also significantly improve the rolling resistance. So this kind of curve represents the progression of the rod depth in this kind of simulated lab rolling test. Okay, so for this kind of measurement, they see that the rod depth occurs at a so slow rate than the matrix with our modified binders. So these are some findings we got from the lab experiments. Now, and then we extended our study to include a more, a very special asphalt binder, which we should call it the epoxy asphalt. Epoxy asphalt is kind of very different from the regular asphalt binder in that it is a thermosetting binder, in that it reacts when the two components of the material are mixed, so then it starts an irreversible chemical reaction. And then you all have experience with epoxy right now. So when the epoxy cures, and it forms a very high strength. So when we mix epoxy with asphalt binder, and after epoxy cure, then epoxy forms a very strong three-dimensional skeleton structure, in which the asphalt binder is built. So when this is used as a binder, and it shows a very good field performance, right? And the epoxy asphalt has been used on some special projects. Applications mainly at the surface material for long-stem also the topic steel and bridges. And it was used in like San Francisco, like the Golden Gate Bridge and the East Oakland Bay Bridge and some other bridges in the United States. But it was primarily used in the last 2 decades in like East Asian countries like in China and in Korea and some other countries. But it has not been widely used on low pavements, mainly because of the high cost of this material. Okay. But we do want to extend the application of the epoxy asphalt to low pavements. So we're going to include this material in the lab test, and we'll figure we can mix this epoxy asphalt with open grade asphalt mixed aggregates, and we found that the use of the epoxy asphalt in porous asphalt mixture can significantly reduce the rubbing potential or improve the resistance to the rubbing. Yes, you can question.
Yeah, is it the epoxy asphalt considered a rigid pavement or flexible?
For asphalt, like an asphalt or asphalt. Asphalt is asphalt. The typical modulus range for asphalt mixture of the asphalt is 1,000 megapascal to 10,000 megapascal, depending on the temperature and the rolling frequency. But the typical modulus of cement concrete is 30,000 megapascal. But for this one, if you are asking for the modulus of the epoxy asphalt, then it's kind of in between. The modulus is like maybe 15,000 megapascal. It's in between the regular asphalt mixture and the cement concrete material. Okay. So some findings are published in some journals papers, and So we did see the benefit of using epoxy asphalt in porous asphalt mixture to significantly improve its durability. And also there's some potential results ultimately related to rotting. The use of epoxy can significantly improve the resistance to rotting. Now, but why don't we use this? There's some factors that prevent us from using epoxy on a large scale on low pavements. The main reason is that it's very expensive because the cost of epoxy asphalt is almost 10 times the cost of thermoplastic from the even polymers for the diameters. And if we consider the cost of the mix containing epoxy asphalt and the mix containing regular asphalt binder, then the cost of mix containing epoxy asphalt is about like two or three times higher than the cost of regular asphalt mix. Now, and another issue that some other consideration that prevent us from widely adopting the epoxy asphalt pavements, that the recyclability. Because now this is a bigger concern that we wanna because of the depletion of the good pavement construction materials, and we wanna reuse the pavement material as much as possible, and this has become a common practice. Right? We have been using the reclaimed asphalt pavement materials very widely in many states, in all the states in the United States and in many other countries. But for epoxy asphalt, that it's a thermal setting material. It does not melt after you reheat it. So whether or not this epoxy asphalt mix can be recycled, then it's a big question. So to address these concerns, so first to reduce costs, there's some practice that have been proposed by some other agencies like the New Zealand transport agencies. They propose it to dilute the commercially available expensive epoxy asphalt with regular cheap asphalt binder, so that to reduce the total cost while still maintaining some level of performance of the binder. Another project that we proposed in our study is to develop some alternative epoxy asphalt binder materials based on its bio-based material, bio-based source of material. And also we at the initial study, we can assess the recyclability of the epoxy asphalt in the lab. So our work on the development of the bio-based epoxy asphalt binder. So we call that the bio-based epoxy binder as a beer. Okay, so we tried a couple of my former students and tried different combinations of the component materials. Okay, so we took the finding from the chemical engineering. So the chemical engineering kind of did all the work trying to find out what the bio-based epoxy material. So we took the finding from the chemical engineering on that development on the bio-based epoxy material, and when we mix them with the asphalt, and including with some curing agents. So we tried different combinations of the bio-based epoxy material, like specifically such epoxy like the soybean oil, and with asphalt and with several curing agent alternatives. And eventually we tried several different combinations, and we find out the best combination, which we evaluated the performance in terms of the change of the viscosity of the mixed material, because that's a key product which reflects the level of curing of the epoxy soybean oil and the curing agent in asphalt. And here we see some results like for this sample, for this formula, the reaction is very quick, so the viscosity increases very quickly over time. So this is not reliable. We want to control the reaction time so that we have enough time to mix components and to lay on and compact mix. And for the other formula, we see that the curing rate is much lower. So we kind of tried different combinations that we have tried, and we found out the different combinations of the components that will lead to different curing rates. And we kind of picked the one that matches the desirable concerning time in the field. And And then, I mean, the details are, I did not include the details of formula here, but it's a mix of the bio-based soybean oil and the malate and hydrate and some, and then the asphalt. Yeah. And then we took that optimized formula and mix the with aggregates, and there are some parts as well mixture specimens, and we evaluated the properties of the PAM parts as well mixture specimens in terms of in terms of permeability and durability and the internal strength and the cracking resistance and also we include the different aggregation in bases, and then found out the best combination from the aggregation and the formula next average size of 4% by millimeter and with the bio-based epoxy asphalt and the results are published in that paper. But there's still room for improvement, and there still needs some additional work to be done to further improve the performance of that formula. Now, our second concern, we kind of looked at one of our previous students where I worked on this part. The second concern to assess the recyclability of the epoxy asphalt mix. Okay. So basically, we kind of artificially produced the reclaimed porous epoxy asphalt mix material in the lab, and then mix the reclaimed epoxy asphalt mix material with new aggregates, new asphalt, and then evaluate the performance of this material. Okay. And here, to see some results, the marginal stability, which reflects the overall stability of the compact mix, and indirect tensile stress, and also the tensile stress ratio, which is used to evaluate the moisture resistance of the mix. And the overall finding is that the incorporation of the reclaimed epoxy asphalt material in new asphalt mixture does not negatively impact the performance of the quality of the mix. So this kind of gives us some assurance that we may proceed with further work to include to promote the use of epoxy asphalt on road pavements. Okay. Again, further work can be done along this line. Okay. Now coming back to the porous asphalt mixture, so the lab study lab experiments can address the different aspects to improve the durability, and also some level of the performance. And next, we want to, the lab study, compared to the field study, the lab study is less time consuming, but still it takes time. And we prepare the specimen and to test the specimen in the lab and still requires quite a lot of time and the labor. Now, we want to take advantage of the data we back from the field and from the lab. So that there are some models that we can use to predict the noise performance, sound performance of the process of making materials. And so if we have such a model, then we can predict the noise performance of new mixture designs. Okay. And so, but the noise performance or the sound absorption performance of the asphalt mix is a very complex phenomenon. Okay. So we will not be able to develop an idea of theoretical model. So what we do is we took the approach that in between the mechanistic model and the input model. So we call that the mechanistic model. Like what we do for payment design. In current payment design, we use sort of mechanistic input model, okay, for predicting the payment performance. So so here eventually we want to predict the type payment noise, because that's the noise that is generated in the field, right? And then in particular, we want to predict the type payment noise in terms of the OBSI, it's noise, sound intensity that is measured by 2 microhertz near the interface of the payment and the type. Okay, and And well, the input variables we want to have is the sound absorption, which can be measured in the lab or can be hopefully we can predict the sound absorption from the design parameters in the lab. And the macro texture, which can be measured in the view on the surface. Yeah. And which can also be hopefully can be predicted from the mixed design parameters. Okay. So this is what a measure of the macro texture looks like. This is again, this is like a picture of the porous asphalt mixture surface, and when we apply the laser scanner on top of it, and this is what we get. Okay. From that, we can calculate the macro texture in terms of the MPD. And now, first, we want to predict the type of noise in the field from the sound absorption and the macro texture. Okay. Of the mix. So so first we want to see whether or not it's feasible, okay, whether or not there's some correlation between the OPSI in the field and the sound absorption that is measured can be measured in the lab. Okay, and when we took the data set from the field, from the field study, and we kind of check the correlation between the sound absorption that is measured in the field and the OPSI, sound intensity that is measured in the field, and the sound absorption that is measured in the lab on porous measurements. And we found that there's a good correlation between the sound intensity in the field and the sound absorption in the lab at certain frequency stages, particularly at high frequencies in terms of the 1,250 hertz and 1600 hertz. At high frequencies, we do find a good correlation. And also we checked the correlation between the sound intensity measured in the field and the macro texture measured on the surface, and we'll also see a good correlation between these two. Okay. So this going to give us some confidence to develop sort of the mechanism in the model. Okay. So now, we will first really develop a model that can predict the sound absorption based on the mixed event parameters. And for this one, now this is here I cannot make this representation of the distribution of air voice in a mix in the porous asphalt mix looks like it's irregular in terms of the shape and the diameter and the size of the pores. And for this one, it's very difficult to predict the sound absorption. Okay. So we're going to simplify it. So we're going to simplify this to such a structure in which the pores are kind of perpendicular to the surface of the layer, and they have the same diameter. Okay. So with this simplified pore structure, then we have theoretical solutions regarding the sound absorption, and the theoretical solutions have been developed by people many years ago, like the Swift and the Thornton model, can be used to predict the sound absorption. And here are some details regarding the model. So the alpha represents the coefficient of sound absorption. It can be measured by, can be calculated from the some pressure at the interface of the material and the air. And now these are the details, and then I'm going to go through some details, and these are some further details regarding that model. So in this model, there are three parameters regarding these pores. One is the length or the height of the porous layer, and the second one is the diameter or the radius of each pore, and the third parameter is the overall gravity, the percentage of the air voice in the mix. So these three parameters are needed for this model. And what we do is we prepare the specimens, porous asphalt specimens with different aggregation, with different alcohol contents, and with different so that with different signatures. And we measure the sound absorption using the impedance tube, and then we use that model, the Wigan custom model, to predict the sound absorption, and then by adjusting the three parameters, porous, porous, and porosity, and so that the differences between the predicted and the measured sound washing is minimized in terms of the sum of the square differences. Okay. And with that, by doing this, we can estimate the values of the three parameters of the model from the lab test data. So, so we estimated the theoretical model parameters based on lab test data, and then we next step is to correlate these three parameters with mixed design parameters like the variable content and the aggregate like that. And then we use some machine learning methods, including the ranking trees and automatic models. Okay. Now, the limit in our study is that we have limited set of data. Okay. And the input variables from the mixture design perspectives are the nominal maximum average size and the aggregation in terms of percent passing different seed sizes and the finance modulus and the finance type and finance content. Okay. And the vast models were selected based on the maximum like R square, minimum C sub P, and the minimum BIC criterion. And here are the models that we eventually came up. These are input models. Okay. So input models for these three parameters of the theoretical model. Okay. So they are basically mainly based on the multiple linear regression model. Okay. And now that's for the sound logic. And for the macro texture from the main profile depth NPD, we also came up with a simple model so that we can predict the NPD macro texture based on the mixture design parameters like the nominal maximum average size. Okay. So with this, so then we combine the model for the sound washing and the model for the macro texture, and then so that we can use these two parameters to predict the noise that is measured in the field in terms of sound intensity. And again, we use a multiple linear model for that. And this is the final model that we developed. So with this, we can and we can plug the model for the sound washing coefficients and the mean profile S that we started in the previous slides, so that now we can predict the actual noise that is measuring field from the mixed design parameters in terms of maximum average size and some band contents and the finance modulus and nominal and some percentage partial number 2, number 4 seed size and also layer thickness. Okay. So that with that we this data give us capability to evaluate different designs of the process mixture to optimize the some performance. Okay, so some general recommendations for the design of the process mixture include first we still need to follow a regular design procedure for process mixture, which is primarily designed to reduce the hydrogen potential to reduce the water film thickness. And so with that, once that performance is guaranteed, then we look into the optimization of the mix design for noise and reduction. Okay. So some general design recommendation that we want to select a smaller nominal maximum average size, like 4.75 millimeter, and we want to use a lower percentage passing the number 4 seed size, and we want to use a lower percentage passing the 2.36 number 8 seed size. Okay. And while with that, we need a guideline to select aggregation, and with that, and then for the first next step is to select the panel type and to determine the optimal panel content. And this is going to use the information we obtained from the previous batch study. Probably we want to use a polymer modified binder, or we can use Epoxy as a binder. Okay. And some linear study that was done by another previous student we want to improve the sustainability of the actual mix by incorporating the renewable materials. Here in Florida, we do not have good aggregate source. Here in Florida, the aggregates that are used in construction pavements mainly imported from other states, other countries. Okay. but we do have a supply, good supply of the seashell material. So, and the seashell material, I mean, when they are broken, they have high angularity. So our assumption is that if we include the seashell material in the porous asphalt mixture, they may change the distribution of the airways. So may affect the sound of washing performance and may affect the noise performance of the cables. So we're gonna look into this and we're gonna prevent specimen of the porous asphalt mixture with different content of the different sizes of the shell materials, seashell materials, and then we evaluated the sound of the washing using the impedance tube, and these are what the tube that was given by students, including standard and other students. Yeah. And I would also measure the other performance in terms of like resistance to rubbery and the inlet transference, and the general findings are that the incorporation of a small percentage of seashell material will not significantly actually impact the performance of the porous asphalt mixture, but it will reduce the permeability to some extent. Okay. And also we reduce the thin surface macro factor. Okay. And so you will reduce the airflow content and permeability. But from that perspective, it's not good for noise reduction. But it will reduce the macro texture from this perspective, and it's beneficial for reducing the type of noise. So when we include this both, and also we also measure the sound of the washing of the paper mixture designs in the lab. And so when we include both physical information of the impact of the seashell material in the porous asphalt mixture on the macro texture and on the sound of the washing, and we plug that both information into the model that we developed previously, and we can predict the overall sound intensity, the onboard sound intensity. And we found that these are the findings that when at a lower percentage of the seashell material, then the small average size process material will have lower type of noise with the increase of the seashell material. Then the larger normal average size process material will have a significant reduction in some of the type of noise. But we see some benefits of the use of the seashell material in the process material with larger average size here. All right, I'm running out of time. So I just give you a very quick instruction about the work that was done by me and my team over the last 10 years along the line of porous asphalt mixtures. And some of the studies actually was supported by the USDOT, UTC, particularly the CTAC, the Center for Transportation, Environment, and Community Health. Okay. And the work is not done yet. I mean, we still have further work being further work down. Is on the way right now. We're looking at some other perspectives of incorporating like the recycle of aggregates and the municipal solid waste incineration brine actually into the porous asphalt mixture about some other asphalt materials. So with that, I think I'm running out of time, and I think this is about size. So thank you for listening to us.
Thank you so much for the very comprehensive review of the study in the mind. Any questions from the audience in the room and also the audience online? The audience online, if you have questions, you can put your question in the chat. Or you can unmute yourself and ask a question. For students. How about online attendees.
And then like more information you want regarding the material, I don't know, I will show this guys quickly. We try to implement some of the findings, but it's POPs are very cautious. Next step is going at least to include some limited and a few tests, some of findings. For some of I can pretty straight up in like a materials office like every year, actually persuade them to influence some designs. The change of personnel in the office, work. But it was some of the findings that we were implemented on test sessions in some. We are interested to see what the results will be in a couple of years.
Okay, great. If no other questions, Dr. Lu is here, the comments, so sure, just give and to make the pigments materials and the design. I think. Okay, let's give another round of applause for the opportunity.